Welcome everyone.
Yeah.
This is the Sustainability Club and We Engineers event with our guest presenter, Dr. James Conca here. We're recording this, so we'll have this on YouTube for people who can't make it later, and we can share it later. And then you can ask questions throughout. He's willing to answer as he goes in the chat or in, just on voice if you want to jump in and ask questions. Sierra, Sean, do you want to say anything before we begin?
Just happy to have you guys here. I'm excited.
Excellent, thanks. That's great.
Okay, well then without further ado, thank you, James. Please go ahead.
Jim. Yes.
Sorry.
So did you want to introduce me or want me to just jump off here?
Just go ahead. I mean, if you want to talk a little bit about your own background and things, we'd love to hear some of your experience and such.
Okay, well, let me actually share the screen a little bit, and then we can see the first slide that has kind of what I've been doing over the years. Yeah, I started out as a planetary geologist, of all things, planetary surface chemist, and that was cool. And then when I was at NASA, first job, the Challenger blew up in 1986, and so did a lot of us youngins' jobs. And so we went searching for other things, and it's funny that many of us from NASA ended up in nuclear. Now they're both kind of out of the box thinking, and so it's closer than you might think, and especially now with the push for nuclear power in lunar and Mars bases, which we will have. It's a kind of a neat circle that I've come through. So then I came up to work at P&L, Pacific Northwest National Lab, with Judith Wright, my spouse and colleague, and started working on a variety of things, but especially nuclear waste disposal. That was the big thing in 1987, and then developed a couple of technologies that DOE asked us to spin off companies on, which was interesting. You know, small business was a great checkbox for DOE, but I'll tell you, small business for a scientist is rough. If it's not Velcro, it ain't worth it. So, you know, too specialized kind of thing. So then after 5 years, success, we packed it in and went to Los Alamos. So I worked at Los Alamos for 6 years, and then became director of the Environmental Monitoring Center around WIP. Does anyone know what WIP is? Waste Isolation Pilot Project in New Mexico. We actually have a deep underground nuclear waste repository that's been filling for 20 years. Now it's only licensed for bomb waste. That's okay, but it was built and designed for all waste. It just got, again, weirdly political in the 1980s. And so it was just, supposed to take everything, and it would have solved everything because it's the greatest rock you could possibly have for this. Half mile below the earth, this massive salt deposit where it takes water 1 billion years to move an inch. That's where you want to put something away forever and ever. So anyway, we've been doing that unknown to most people because no one knows what transuranic bomb waste is anyway. So I was down there for a while, and then came back to the Hanford site here. And then in a bizarre twist, I used to take people, congressmen and stuff, down hole into WIP to stand in front of nuclear waste. It's like, this is a piece of cake. What's the problem here? And they loved it. And I took an editor from Forbes down, and he said, "Gee, you want to write for Forbes?" And I went, "Huh? I don't even have a Twitter account." He said, "You will." So I do. And that's kind of started the Forbes thing, which has been very bizarre and interesting. It's not at all like writing, scientific papers. In fact, the first one I did, he said, "Jim, you sound like Wikipedia. Could you get an attitude?" And I went, okay. So I have an attitude now. Sometimes it backfires, but it's pretty funny. Yeah, but it's also been very enlightening on how to talk to the public about these issues. So yeah, I've been doing this for some time now. It's kind of interesting. So if you have any questions on any of these subjects or almost anything else, concerning energy or nuclear, just Google Conca Forbes and then whatever subject, and I usually should pop up in the first page. So that's kind of neat. But so that's kind of what I'm doing now. We're both retired and living up near Hanford, near the most contaminated site on Earth. Not. So, I mean, it's no big deal. I mean, nothing from Hanford could ever get out of Hanford. Even if you walked away from the tanks, they'd have no effect on human health or the environment. But it's very hard to talk to people about that because they've been told it's, the worst place on Earth. So let's just dive into this. So the big question is, can we achieve a new zero carbon energy mix by mid-century? And what would that look like? So that's the whole point. But I do want to just throw out President Biden's infrastructure bill and what it means for nuclear. The infrastructure bill was a $1.2 trillion bill, and it has $25 billion for nuclear. It's not a huge amount. It's not bad. Nuclear usually just gets chopped out. So $3.2 billion to demonstrate new reactors like Bill Gates's. Bill Gates owns a nuclear company. You know that, right? Everyone know that? So yeah, it's in Bellevue. It's neat.
It's in the news lately, actually. Yeah.
Yeah, it's been in the news. His natrium sodium fast reactor, kind of interesting. And then of course there's the Corvallis new scale small modular reactor, and we'll talk a little bit about those. And then there's about $21 billion to demonstrate things. One, to keep existing nuclear fleets open. I mean, this is the stupidest. This is the stupidest thing in the world is to shut down perfectly running nuclear power plants because they're a penny more kilowatt hour than gas. I mean, who cares? I mean, it's like, here we are trying to decarbonize the world, and a penny a kilowatt hour seems to be too much to keep nuclear open. That's one of those hypocritical things. And then a whole bunch of other stuff. So there is a push because all of the leading climate change scientists like Jim Hansen, Kerry Emanuel on down say we will not solve the climate issue at all without a vast expansion of nuclear power. So just forget it. If you're anti-nuke, you're not serious, you're not doing your homework, and you're just listening to nonsense. Because if we don't, then we're screwed. So so that's kind of where that stands. Now, the nice thing about this infrastructure bill is that it defines advanced nuclear in the clean energy category. And that's been a fight because the anti-nuclear people do not want nuclear to be categorized as clean, even though it's cleaner than almost anything else. Okay, now, in order to have a grid, okay, so we have an electric grid in this country. We have actually several pieces that are slightly connected. Electricity is simultaneously, and it has to be simultaneous. It's produced, it's delivered, and it's consumed. If you produce more than you consume, you start blowing transformers, the big ones, the ones that cost $400 million. If you consume more than you produce, you start having rolling blackouts. So neither of those are good. And so the grid operators, the independent system operators or the regional transmission operators, like BPA, the Bonneville Power Administration here in Washington State, they constantly monitor the grid and they plan as far enough ahead in time as they can to make sure this is all simultaneous. Otherwise, they're going to have problems. And we've never had problems in the Pacific Northwest until now. Because we have so much hydroelectric. Now, the other thing, so just remember that, it has to be simultaneously balanced at all times. Then there's something called a capacity factor. And I'm curious to see how many people know what capacity factor is. Capacity factor is the annual average percent of the time, or percent of the maximum output possible that actually is produced, okay? So that means nuclear, it just doesn't shut down except to refuel every 2 years. So it's very, very high capacity factor. It's putting out, say, a 1,200 megawatt nuclear reactor like is next to me over here in near the Hanford site, Columbia Generating Station. It produces 1,207 megawatts 93% of the time. And that's pretty good. You can depend on it. Natural gas only runs about 56% of the time. And there's reasons for that. It could do more if you wanted to, but it's expensive, contrary to what you think. Coal only runs about 50% of the time. Hydro about 40% of the time, because there's so much demand on the water in the hydro system. It's not just to produce power, it's for flood control, for irrigation, for transportation. So there's a whole bunch of reasons the water is not only producing power in hydro. Wind is about 35% of the time, but it's very dependent on where you live, where they are. And solar is about 25% of the time. Now, in Eastern Washington, where all these wind turbines have been built in the last several years, the capacity factor is only 27%. Okay, in Washington State. In Tornado Alley, in the mid part of the country, where obviously by the name, they get a lot of wind, the capacity factor for wind is 45% of the time. Now that is a major difference and very, very good. So if you're going to be building wind turbines, as many as you can, you need to be building them in Tornado Alley, not in Washington State. They're useless here, and I'll get into why. So that's what capacity factor is. Now, if you have the installed capacity, so you build a 1 megawatt wind turbine, okay, then you multiply that by the capacity factor, so 0.348 times 8766 hours per year, and that gives you the amount of power produced per year by that unit. Now, installed capacity doesn't mean very much because you need to know what the capacity factor is. And the amount of power it could produce if the sun shone 24 hours a day or the wind blew 24 hours a day doesn't matter. It only matters what it actually produces per year. So if you compare something like a 1,000 megawatt nuclear power plant with a capacity factor of over 90%, it produces this much, 8 billion kilowatt hours a year, or 8 million megawatt hours a year. Okay, that's just what it does. A little bit more, a little bit less, depending on what's going on that year, but it's pretty much about 8 million megawatt hours a year. Wind, same installed capacity, only produces 2 million. Okay, so it's about a little under a quarter. That's important because when you say you're installing 1,000 megawatts, you're not really installing 1,000 megawatts of wind. You're kind of installing 1,000 megawatts of nuclear, but you're only installing 270 megawatts of wind. So when the state legislature or the power companies talk about we need to install 10 gigawatts in the next 5 years, you need to remember you have to multiply that by the capacity factor of whatever you're installing in order to get it right. So remember this, very, very important. Now, even more important is that over the lifetime, because nuclear design life is 80 years, not 40. 40 is an arbitrary licensing period. The design life is about 80 years for the generation 2 nukes, about 150 years for the big hydro. Wind is only about 25 years. So if you multiply that yearly production by the lifespan of the unit, you're going to get a real difference. So a 1,000 megawatt nuclear plant is going to produce over 10 times the power of the same installed amount of wind. Okay, this is actually quite important. Now, I love these NASA nighttime shots, not just because I worked for NASA, but you can tell right away who has energy and who doesn't. It's what the fighting's always been about, what it was always be about. So this is what it looks like at night from space, from the generation of 24 trillion kilowatt hours a year, which is what humanity produces about now, although it's continuing to go up. It's going to pass 35 trillion kilowatt hours a year by 2040. And I'm going to use kilowatt hours as a unit, excuse me, because that's what we pay at the end of the month. When the bill comes, we pay for kilowatt hours. And Washington State has the cheapest power almost in the world, 8 cents a kilowatt hour. Now, by comparison, New York right now is 18 cents a kilowatt hour, and Hawaii is 35 cents a kilowatt hour. So again, Washington State is very cheap because of all the hydro we have in this one nuclear plant, and the fact that we are a regulated market. So the energy companies cannot gouge you when things go bad, like they can in Texas and California. Now, this is the distribution of electricity generation or power and transportation globally. So this is the worldwide present energy distribution. It is 2/3 fossil fuel and 1/3 split almost evenly by everything else, but especially hydro and nuclear. Transportation, which I won't talk about much tonight, is still almost all petroleum. And that's the problem, because 1/3 of the emissions globally come from the transportation sector. And if you don't replace petroleum, especially with electricity, which is a much cleaner form of energy, I mean, a much more efficient form of transportation fuel, and you produce it without coal or gas, then you're going to be stuck with petroleum for the next 50 years or more. Now, hydrogen's great, all these alternative fuels, it's great, but electricity is the only thing we will be able to produce in abundance, enough to make a dent in petroleum consumption in the next 30 years. And that means a lot of electric vehicles, and that has its own problems, which we will talk about a little bit. Now, the United States, also 2/3 fossil fuel, a little bit more nuclear, a little less hydro, a little bit of wind coming up. But yeah, so it's been 2/3 fossil fuel for the last 40 years, and it's going to be 2/3 for the next 40 unless we make some radical changes. But it really depends on where you live. Washington State, again, the least fossil fuel state in the Union. West Virginia is the most, and Illinois is the most nuclear. European Union, a little bit more nuclear because of France, a little less hydro. Korea, almost 30% nuclear. It's going to go, their plan was to go to 60%, just like Japan's plan was to be 60% nuclear by 2040. Now, Fukushima put a hurdle in that way. We won't talk about much about that unless you want to. But the reason Korea and Japan were going to be over 50% nuclear is they have no resources to speak of. They have no fossil fuel. They have no wind resource. They have no solar resource. They have no biomass resource. So unless they want to be completely dependent on places like China and other countries for their energy, they should go nuclear. That's what their plan was. When they get over this, there will probably be their plan again. Now, China doesn't look like much, 4% nuclear. It's still mainly coal with significant hydro. They are frantically trying to change that. They're breaking ground on a new nuclear power plant every month. Their plan, their latest 5-year plan, calls for 180 large nuclear power plants, big ones, by 2035. And they probably will do that. They usually stick to their plans. So they are going to dominate the nuclear power world unless we step up. And they will do it because they know it. They need it. Now, at the same time, they need so much energy anyway that they're still building coal plants. Okay, modern ones, and they're shutting down the really dirty ones, but they're building more renewables than anyone else, and they're building more hydro. They just need a lot because there's 1.3 billion people, or 1.4 billion people in China, and they need energy, and we'll talk about why. Now, in fact, let's talk about why now. This is the world power consumption growth curve. It's very steep, has nothing to do with the United States. We're 4 trillion kilowatt hours a year and kind of flat. Last century was all about us. This century is not about us. The world I mentioned was presently at about 24 trillion kilowatt hours. So if we're going to go up and up, or are we going to turn over at some reasonable amount, what that reasonable amount is, and we'll talk about that. However, say we do limit it to something like 34, 35 trillion kilowatt hours a year, that means to get that and to address any of the environmental issues we seem to care about, then almost 20 trillion kilowatt hours of new energy new electricity has to be produced by non-fossil fuel. Now that's more than all of fossil fuel now. Okay, so the numbers are big, and you got to remember the numbers. They matter. Okay, and again, don't talk about percentage. I don't care that wind has increased 50% this year. 50% of what? And 50% of almost zero is still almost zero. Okay, you need to say how much power is produced. How many kilowatt hours is it producing? Because that's what counts, not percentage gain. And we'll talk about that. Now, the reason that curve is so steep is because of these people. 1.2 billion people still have no access to electricity. 80% of them are in South Asia and Sub-Saharan Africa. 2.4 billion people still burn wood manure as their main source of energy, and 3 billion more people will be born by mid-century. That's a lot of people. And you might say, well, okay, forget about it. Don't give them energy. We have all we need. We care about the planet and the environment and blah, blah, blah. So don't give them any energy. Well, that's cruel, because it turns out it takes about 3,000 kilowatt hours per person per year to lift someone up out of abject poverty. Remember that number, 3,000 kilowatt hours per person per year, to move them into what we think of as the middle class. Now, COP21 now, as of last week, is COP26. All the really important discussion is about how to give these people 3,000 kilowatt hours per person per year without giving them coal, and who is going to pay for it. Those are the only two questions that matter. And this is the only way to eradicate global poverty. Now, that's very, very important, because there's a dynamic tension between the environment and human health. And that's kind of summarized in something called the Human Development Index, the United Nations Human Development Index. So I encourage you to Google UNHDI sometime and look at it. What it says is that access to energy is the first term in the equation of happiness. And that's true, okay? Everything else is secondary. And it doesn't matter whether you're a 17th century nobleman that was getting the equivalent of 3,000 kilowatt hours per person for him and his family, off the backs of 10 slaves, 10 indentured servants, 4 oxen, and 4 horses. That's a great calculation for the student. You should do sometime. Or it's everyone listening to me here, which is getting about 12,000 kilowatt hours per person per year off the back of hydro with some nuclear, a little bit of other. It doesn't matter. You need at least 3,000 kilowatt hours per person per year to have what we consider a good life. So when we look at up here, these groups, the haves, the developed world, if you want to use the right term, we have a lot of energy. And so when we talk about addressing climate change, we talk about moving us down, cutting energy use, becoming more efficient. And, we can do that. Japan, now it's less than 10,000 kilowatt hours per person per year. In 1992 was 16,000 kilowatt hours per person per year. They have been screaming down, mainly because of technology. And again, technology is great. It's wonderful. The UK is probably the best. They're at about 6,000 kilowatt hours per person per year. I put California as its own country. That should get a laugh. But California is great, but it's half of it is quite warm. All right. Now Canada, big and cold. There's no way Canada is going to come down at all, and that's okay because they don't need to. There's not that many people there, and they don't affect the globe as a whole. Who affects the globe, of course, the United States, China, India, and Indonesia, the big population centers that are growing. And so, if we look at China, it's kind of bizarre. It doesn't look that good. Oh, I'm sorry. Let me back up a bit. Sorry. The x-axis is annual electricity use per person, so per person per year. The Human Development Index goes from 0 to 1. 1 is heaven. Okay, it's really wonderful, and that's why everyone wants to come to the developed world. You would be insane not to, because that's where life is good. If you're below 0.4, life is absolute hell. It is really difficult to live. You spend 6 hours a day just getting water. Okay, so yeah, a little bit of energy, a little bit of tubing and things like that, and wow, your life could become much better if you had a little bit of energy. Now, China doesn't look that great. It's below 0.8. But there's two parts of China. There's 800 million middle-class Chinese now, 800 million. And there's 600 million still in poverty. And so if you look at China's 5-year plans, you look at their policies, both economic, political, military, doesn't matter what it is. It's to move these 600 million up into the middle class by mid-century. Now, it turns out, I don't have a lot of time to talk about it, but it turns out that your military and economic strength derive directly from the absolute number of middle class in your society, not the percentage, the absolute number. And the United States dominated the 20th century because we had more middle class, 200 million for most of the second half of the 20th century than anyone else. We dwarfed the rest of the world in terms of the middle class. Now they've caught up and China has now passed us. So by mid-century, and they've done it quickly, they did it in about 18 years. So if anyone wonders who is going to be the economic and military powerhouse of the second half of the 21st century, they need to pay attention to this, because China will have 1 billion middle class. Now, we don't all need, there is kind of a sweet spot here, okay? We don't need thousands and tens of thousands of kilowatt hours per year per person. That's a waste. We don't need that. So yeah, we need to bring all these people down, but we need to bring all these people up. So there is a zone between about 4,000 and 6,000 kilowatt hours per person per year that is the most efficient at eradicating global poverty and its evil stepchildren, war and terrorism. It's the only way to do it. You need to produce enough energy to get everyone up here, and we can cut ourselves down there. Now, how much is that going to take? Well, it turns out, yeah, the industrialized world, sure, we can cut us down to 6,000 kicking and screaming, but there's only 1 billion people in this subgroup. Now, there's a lot of people at 3,000, keep them there, that's fine. The developing world, the existing developing world, has to increase to 3,000. That's going to take 15 trillion kilowatt hours a year. And those born by 2040 are going to have to get their own 3,000. So that's 10. So just these two groups alone surpasses what we produce now in all energy for the entire Earth. And so the minimum amount of energy required to eradicate global poverty and get everyone up to a good life is about 33 trillion kilowatt hours. And it's going there. It's been moving very, very fast. When I started doing this in 2007, we were only at 15 trillion kilowatt hours. Now we're at 24. And by 2040, we'll be at 35. All right, let me back off and talk about climate change. This, excuse me for this very complicated graph here. This is climate change over the last 500 million years. Okay, now the scale changes in order to get everything on. So here we are thousands of years, tens of thousands, hundreds of thousands, millions, tens of millions, hundreds of millions. All right. Now, what should jump out at you right away? What do you see? Anyone?
Changed a lot over time on Earth.
Yes. And right now, the last 10 million years has been very cold, incredibly cold, unusually cold. So much so that for the last 2 billion years, we've had glaciation. And glaciation is a rare event on Earth because you need to have plate tectonic positioning so that there's land masses at the poles. Otherwise, you will not get glaciation. So this is all combined for the last 2 million years to give us a very cold Earth. So in the past, it's been a lot warmer. CO2 concentrations have been a lot higher. It's like, okay. And a lot of times you hear people say that. It says, well, hey, it's been higher in the past, so what? We can deal with it, right? It's no big deal. Well, it is a big deal because it's not the absolute temperature and it's not the absolute concentration of CO2 in the atmosphere. It's the rate of change. So if you look here in the last 150 years since the Industrial Revolution got going, we have been raising the temperature rather quickly. And again, especially if you look at the different scales here, this is expanded. If you compressed it to what it is back in the Permian or something, this would be a straight line. I mean, it would just be a straight line, vertical. And so what happens, the biota doesn't like change, okay? I don't like change. My cats don't like change, all right? If you change too quickly, things die. It's called extinction. It's no big deal unless you're the one being extincted. But that's what happens. It's simply too fast, too quickly, and things die. So that's what's going on more than anything else. It's not the absolute temperature that matters. It's the change in the temperature. Now, if you look at the climate change models, I apologize for throwing this up there, but there are two end member models that everyone talks about. One is A2, which is business as usual. Nothing happens. We still go on being 2/3 fossil fuel right to the end of the century. Or B1, meaning we make significant reductions. Everything we want to do that we can do, like if all of the promises made at COP26 go forward and are successful, this is what we get. Now, it's not that it's perfect. We're never going to go back to the 1850 reference temperature, not for a long time. So your choice is between these two extremes, all right? And so how well you execute your decarbonization plans just simply puts you somewhere between these two end members. And then the slop, of course, the uncertainty. So, if you're doing really well, you could keep it to 2 degrees Fahrenheit, which is this 1.5 centigrade number they keep throwing up. Or if you don't do well, then you're going to be 8 degrees Fahrenheit or 4 or 5 degrees Celsius, and that's not good. That would be not good. So again, all the COP meetings, this recent one in Glasgow and the one in Paris, is about who's going to pay to implement B1. Okay, this is not trivial. The estimates for the cost are in the multiple trillions. So decarbonizing the world is a big lift. We can do it, but it's a big lift. So in the United States, I show this map because here's Washington State. So again, if we actually, successfully implement B1, we can keep things down to a few degrees. Washington State's pretty good because we're ameliorated by the marine climate, especially you guys over there. If we don't, things get rough. Now, another thing you probably hear incorrectly is that higher CO2 gives you higher crop yields. That is not correct. Okay, the crop yield, all things being equal, if all you did was increase CO2, the yields would actually go up. But that's not what's going on. The crop yield is generally a function of the peak temperature during the growing season. And as that peak temperature goes up, the yield goes down. So Washington State, apples and cherries do badly. This is horrible because we are the largest apple and cherry exporter in the world. But grapes and dryland wheat do quite well. So don't worry. Our wine industry is fine. Don't worry. Supposed to get a laugh too there. But yeah, so things change. Things change depending on the peak temperature, what happens to it. So again, everything's, growing seasons are changing, zones are changing, growth zones, agricultural zones in the United States have changed a 0.5 point so far. So what, and of course that's going north. So in 10, 20 years, things that could grow in zone 4 in California will no longer be growing in the same place in California. So we will adapt. We have to adapt, or you die. That's just nature. Okay, last climate change slide. These are the predictions in order to keep the warming to just 2 degrees C. So to keep, to achieve B1, okay, to achieve that successfully, that level of decarbonization, if we started decreasing global emissions in 2011, start decreasing them, we could actually have ended up with a little bit left by mid-century, wouldn't have to fully decarbonize. Well, we blew that one. But so 2015 comes along. Now we have to actually fully decarbonize at about a rate of 5% a year. Well, we blew that one. So 2020, this used to be in the future. Now it's not. Now it's in the past. We needed to start decarbonizing 9% a year. Global emissions had to decrease 9% a year, reach zero by 2040. That's why everyone always talks about 2040. Well, that, I guess the question is, how much are we decarbonizing? How much is global emissions decreasing? Anyone know? Yeah. Anyone know? Yes, you got it. Who was that? Dave.
Yeah, they're increasing.
Yeah, they're increasing. Okay. So, I love it because when all the projections that you see for decreasing emissions, those are simply dreams. Those are desires. Okay. That's in order to meet goals. But if you actually look at any serious projection of what the emissions are going to do, there isn't a single one I've seen where they decrease at all until by 2040. Not at all. And that is worrisome. It's more than worrisome. It means a lot. So what we need to do is get rid of these and bring these up. Sounds easy, right? It's easy. Well, it's simple, but it's not easy. Okay. Get rid of these, bring these all up. And then it gets to this idea that some people don't like some of these. Some people don't like wind. Some people don't like nuclear. Some people want to get rid of hydro dams. This is nonsense. We don't have the luxury of picking and choosing one or two of these. If you don't have all of them, you're going to fail. I mean, it's just all there is to it, because these are too big. There's too much of these. And so you're going to have to bring all of these up quite a bit. Now, what's interesting is that the UN just came out with a study last week that said nuclear is actually not 12 tons of carbon dioxide equivalent per gigawatt hour. It's only 5, which is pretty amazing. 5.1 to I think 6. So yeah, nuclear is actually the least emitting, and this is a life cycle, mining, enrichment, everything else. And most of that comes from cement. Cement is a very CO2 intensive process. So nuclear and hydro take a lot of cement. Wind takes a lot of cement. And so that's where these emissions are coming from, not during operation. Of course, during operation, there's almost nothing for any of them.
Jim, there's a question.
Yes.
Someone raising their hand.
Aha, let me get the chat. Where's the chat? Oops.
Is it Sheknia?
Shekinah.
Yes.
On your previous slide, if you don't mind going back, there were 2 emissions, biomass co-firing and biomass. Would you be able to take a moment to explain the difference between the 2?
I'm sorry, I don't know enough about co-firing or biomass, but it's kind of like combined cycle gas. Okay, you have more than one thing going on at the same time. You're producing energy both from the direct burning and then from the other processes going on, like residual heat, things like that. So I don't know enough about that. I apologize. I should. But yeah, biomass people think is so very, environmentally benign, but it actually isn't. So it also depends on what you're burning and the time scale on which that is replenished. So if you're burning wood, and then you say, well, I'm going to grow forests to replace that. Well, it takes 40, 50 years to grow a forest, even a nascent one. Okay, it takes 100 years to grow a real forest. So if you're burning wood, then you're not going to get that back out for a long time. So again, it doesn't help you in 1,000 years. You can come to some type of an equilibrium with it, but in the short term, you don't get it back very easily. Now, if you grow something like switchgrass, which you can grow every year, then you can, you can be sustainable in that sense. So sorry, I can't answer the question about co-firing. I am going to kick myself and research that tonight.
That's okay. Thank you for the additional context. And then what you were saying previously with the hydro, nuclear, and wind. So those emissions typically come from the construction of
Right.
those. Okay.
Almost entirely. Okay. In fact, I think we'll be getting to that soon.
Why are geothermal and solar so high in CO2 compared to the other?
Because of geothermal, it's because of operations. Solar, it's because of production. You use a lot of organic solvents to make PV cells, huge amount. And just go to China to find the environmental destruction that's causing. But yeah, so it's mainly production in solar PVs. Geothermal, it's mainly operation. Hydro, nuclear, and wind is all construction.
Okay, thank you.
Now, if you talk to the climate scientists in the world, especially the top ones like Jim Hansen, Kerry Emanuel, they've all done this math, and you can't do decarbonization without significantly increasing nuclear, not just keeping it, but increasing it significantly, tripling it, in fact. And what's very weird is that most climate change people are anti-nuke, which is really kind of stupid, but they've kind of that ideologically. I mean, they don't understand it at all. They don't know any of these issues. They don't do their homework. They just have been told that nuclear is horrible and we don't need it. And they've been told over and over that we don't need it. And yet here's the climate guru saying, no, we really need it. So unfortunately, in the world, in America lately, the idea of being a scientific expert has gone out of fashion. It's kind of bizarre. Insofar as everyone thinks they can pick and choose the science they like that fits their ideology. And of course, that's completely anathema to the idea of science in general. So this is a problem. So here's the leading climate scientists in the world saying we need nuclear, and then half of the environmental community says, no, we don't want it. So, and again, this gets back to, we don't have the luxury to pick and choose what we like and don't like amongst the zero carbon sources or low carbon sources. We need them all. Now, the United States is in fact decreasing its emissions solely, and I say solely, because we are replacing coal with gas. It has nothing to do with renewables. And so we are at a 27-year low in our emissions because we have replaced coal with gas so much. Now that's important. It's great, it's wonderful, except gas, will get you so far. In fact, let's go back to, oops. Oh, come on, stop spinning. Okay. Yeah, so natural gas is better than coal, no question, not just the CO2, which is, about 2/3 of it, but all the other stuff, sulfur, mercury, all the other particulates, stuff like that. Gas is really much cleaner than coal, but it's still a fossil fuel. So you're not going to get to a decarbonized future if you retain significant amount of gas. And that's because we have so much gas. I mean, as a geologist, I'll tell you, it's just bizarre what fracking has done. Now, prior to 2006, we did not know how to frack very well. And fracking is just, hydraulically injecting small particulates into a tight geologic unit in order to keep it open so that you can extract gas or oil from it. And it works incredibly well now. We're getting very good at this. And so, in fact, we're getting so good, I want to point this out. This is a walking drill rig. Okay. This is a walk. So from a science fiction standpoint, this is fantastic. But from an environmental standpoint, it's horrible because this rig goes down a mile. I'm sorry. It goes down up to 18,000 feet. But it can put 12 stringers out 1 mile. Now that's incredible. It's not just one drill stem anymore. It's not just one drill hole. You've got 12 stringers off of this one drill rig. And when it's done, it picks itself up and walks to the next site. Okay, this is literally a walking drill rig. So we're getting so good at this, it's very hard to see that we're going to stop it. All right, now this is kind of like giving a bunch of children a bowl of candy and a bowl of apples and saying, don't touch the candy, eat the apples. They're not going to do that. And then leave the room, of course. Not going to do that. It's too easy and too lucrative and too energetic to get gas out of the ground, and oil too. To expect that we're going to stop this without significant political will and alternatives to replace it. So I've set you up for this. What are the fastest growing energy sources in the world? Shout it out.
Gas.
Anyone else?
Oil.
Anyone else? Yeah, you're right. Okay. Okay, it's the three big ones. Okay, fossil fuel. Fossil fuel is the fastest growing energy source in the world. Now, I know renewables are coming up, screaming up there. That's amazing. Nuclear and hydro aren't growing too much, but they're still growing. So the idea that you're not going to increase hydro or nuclear, and you're going to replace these way up here with just renewables, that's insane. It's not going to happen. I mean, it absolutely cannot happen physically. These are still growing, especially oil. So it just, there's no such thing as a free lunch. You really need to understand that. If we're going to get rid of these, you can't pick and choose any of these not to do. I mean, you just have to do them all. So if we just look at, say wind energy to replace coal and oil, not even gas, that's going to take about 20 million megawatt wind turbines, or about 10 billion tons of steel. Now, no one likes to talk about steel, 20 billion tons of cement. No one talks about steel because steel is boring. Now, 10 billion tons of steel. What's the global output of steel per year? A little over 1. Okay, so we're going to do all this. We're going to build 20 million megawatt wind turbines using 10 billion tons of steel, and we only produce a little over 1 billion a year. Is that likely? Are we going to tell everyone you can't build anything else now? For the next 10 years, we're going to be building just wind turbines? It's not going to happen. Or even worse, we're going to, quadruple or quintuple the number of hard rock mines in the world. That's also has its own environmental issues. So again, there just is no such thing as a free lunch. This is a complicated issue. Everything's connected, and the numbers matter. Okay, so how do we do this? Any low carbon plan for power generation that has any hope of achieving the emission goals we talk about in the time frame we need them, meaning 2040, this is the green part of the Green New Deal, must have some form of the following. Now, this is not exact. You need some form of this. Okay, you can play with the numbers all you want, and it's going to depend on a whole bunch of things. But you need to stop building fossil fuel plants. Okay, you just got to stop, because once you build a new fossil fuel plant, like a new gas plant, which everyone loves to build in America because gas is so cheap and it's so easy to throw them up quickly in a year. Once you build a new one, you've locked yourself into that for at least 40 years. So if you build a gas plant, that gas plant is going to be operating for 40 years. You can't shut it down after 10 years. The economics, the politics, everything, you just cannot shut down a perfectly good new gas plant just because you said, oh well, now we're gonna decarbonize. You can't do that. So you have to stop building them. You need to stop closing existing nuclear plants because most of them, almost all of them, have been relicensed for one 20-year period, and they're all safe. They were designed to run at least 80 years. They were only arbitrarily relicensed after 40 and then 20 years after that. Those numbers were picked out of the air by the by the Atomic Energy Commission, AEC, which is the predecessor of DOE and NRC. And that was picked out in the 60s, out of the air, just saying, well, when should we relicense them? Take a really good look at every single component. 40 years, let's just pick 40 years. And that's what they did. Now, the problem is, closing India Point near New York was horrible. It was producing almost 50% of New York City's power. And now what are they going to do? They're going to bring in gas and they're going to pretend they can get most of it from Quebec hydro, but that's going to dry up soon because everyone's trying to get Quebec hydro in the Northeast because they keep closing nuclear plants. So, and the idea that crying, a penny a kilowatt hour is just too much for America to bear is insane because we're going to be spending trillions trying to decarbonize anything. And every time we close a nuclear plant, generally gas replaces it and the carbon emissions go up. So that's, you need to stop this. Yes.
Tim, what is that? Who's crying a penny a kilowatt is too much? I don't understand that reference.
Right now in the unregulated markets, okay, like in the Midwest and in the Northeast and in Texas and in California, gas and subsidized renewables are undercutting nuclear by about a penny a kilowatt hour. Okay, and the states have been trying, to pass legislation. A couple have, like in Illinois, that they give a penny subsidy per kilowatt hour to nuclear. We give 2.5 cents to wind and solar, and so a penny a kilowatt hour is just too much to pay.
Probably get way more than that in subsidies to.
Yes, because we do not add in the gas backup that has to remain on idle while in order to load follow. But we'll get to that. Actually, that's a good point. So again, stop closing nuclear plants. You need to build more new ones, but you need to stop closing the ones we have because they're very efficient and very good. Build as many wind turbines as possible. That's great, fine, but you need to site them in Tornado Alley, where they produce almost twice as much power as they do here in Washington State. And if you look at Tornado Alley, that's why it's called Tornado Alley. These are the average wind speeds. So yeah, if you're going to get more bang for your buck, more bang for your ton of steel, you better put them here. And then you need high voltage transmission lines. Okay, we can do those. But building them where it's green is just dumb.
What about offshore? We've been hearing a lot about offshore.
Yeah, offshore, expensive and difficult. That's fine. We can do as many as we want. But again, when you start putting them offshore, the public doesn't like it. Okay, so the amount of public opposition to new wind is actually quite large when you start putting it in your backyard. This is, this NIMBY thing, not in my backyard stuff. Everyone wants stuff, but they don't want it in their backyard. Well, sorry. Okay, you need to make some sacrifices if you care to do this. So, but without a doubt, Tornado Alley is the best place to put them, and that's why these states have jumped so much with wind. I mean, they're Iowa, this side of the state is almost 50% wind, and that's great because they get a lot of capacity out of it. So again, that's kind of tricky. And the reason you want to do that, put them into Tornado Alley and not Washington State, is that here is the amount of steel and concrete, cubic meter of concrete, which is a couple of tons, massive steel, metric ton per megawatt. This is what it takes. So wind is 10 times more material intensive. And it also goes for things like copper and neodymium and everything else that wind turbines need. But just steel alone and concrete, you need 10 times as much per megawatt hour as you do for anything else. Okay. Now, solar takes a lot of steel, but not much concrete. Hydro takes a lot of concrete, not much steel. Coal, the thermal units don't take much at all. And gas takes almost nothing. That's why you can throw a gas plant up in a year. It just doesn't take any steel or concrete. It's incredible. And that's why state legislatures love them, because you don't have to wait 5 years, 10 years. You you can just throw them up in 12 months once you get them cited and licensed. So that's, this is important. A very, very, kind of a mundane issue, materials, but it's really important when you get to renewables, especially wind. We just don't have the steel or the concrete to do it. And so that's why when I showed the emissions per source, that's why wind was as high as it is, because it's all about concrete. Okay, so, and the same thing with rooftop. So put rooftop solar on all new buildings. I have it on mine, it's great. You amortize it along with in the mortgage, you won't even feel it. And on many existing buildings. But again, you need to put them on in areas that average at least 200 sunny days a year, where you get capacity factors of 35% instead of 20%. My solar panels only have a capacity factor of 10%. That's terrible. I mean, it's horrible. I like it. I wanted some street cred on renewables, but that's not very efficient. Not a very efficient use of the materials that go into producing
And
PV cells.
Where are you located?
Hanford, Washington, so Richland.
That's
Oh,
a
yeah, we have 300 sunny days a year, but we're far north. We're up here, actually in this green to yellow transition zone. You really want to put it down here. Okay, you don't want to put PV cells in Maine. That's just again, that's another dumb thing to do, because you're not going to get much energy out of it, and we don't have the materials to waste in putting them just anywhere. The problem is everyone puts them where they're going to get subsidies, right? It's all about money. So we don't have a plan, and I'm not sure the infrastructure plan bill is going to give us a plan. It just gives us money to do things. But the plan is, where do you do this? You have to coordinate where you're building your new systems in order to get the maximum amount of power out of them. And then we need small modular reactors because they're small. Now, this is kind of funny. The public likes the idea of small. They don't know at all what it means, but they like the idea of small, that it's safer. And it is insofar as when you shrink the core down so far that the surface area to the volume ratio changes so much that you can bleed off heat faster than it can build up and melt down. So it's actually quite nice. If you look at NuScale's design, which I think I have here. Hold on a second. Yeah, so they can't melt down. So generally, SMRs cannot melt down. And we fixed all the other scary things. And unlike most people say, oh, you haven't built one in 30 years. Yeah, well, we haven't been idle. Okay, we have done a lot of testing, a lot of design work. We're ready to start building these things. And there's a few of them. I mean, TerraPower's, natrium sodium fast reactor, that's got a lot of support right now. It's still quite a far distance from reality. It's also very good at backing up intermittent sources like wind, which most SMRs are. Then X Energies is a pebble bed reactor, basically high temperature gas cool reactor. And it can integrate into large electricity regional systems, and it can serve as a base load or to load follow renewables. Same thing with NuScale. This is NuScale is just a traditional light water reactor, just like have been using for decades, and like essentially we use in the nuclear navy. Yeah.
Is that on your site? You had an article about the military developing or getting one of these by 2027. Which one?
They actually not on this. And then I've been told recently that they're kind of scrapping those too. So they're still looking for small modular reactor. Now, NASA has actually chosen their reactor for the Mars and Luna bases, but those are very small. They're like not even 1 megawatt. So most small modular reactors are anywhere from 50 to 300 megawatt units. Okay, and NuScales are about 72 megawatts a piece, and you put 6 or 7 together, 6, and call it a 6-pack, and it's about the same as a large reactor. Okay, so but again, because they're small, again, the surface area to volume ratio is really good. And the power plant itself and the emergency evacuation zone is nothing. I mean, it's basically the fence around the plant, okay, as opposed to 50 miles away that you have to do for existing nukes, and that gets everyone scared, and that's one of the big issues. But again, NuScale is very good at backing up intermittent sources on any time scale, minutes, hours, and days. So if we look at TerraPower's design, again, I don't.
Question real quick.
Yes,
Sorry.
go ahead. No, good.
How does the size correlate with its ability to prevent meltdowns?
I will go over that. But again, the surface area to volume ratio is such that it can bleed off heat at a much faster rate than a normal reactor. And so you can't melt down. You're essentially bleeding off. Now, all of these new SMRs, the core is below ground. Okay. The soil surface is up about here for TerraPower. So again, you have a geothermal heat sink as well, and that helps. So I'll go over that. So this is TerraPower's design. X Energy again is a pebble bed reactor, so the pebbles can't melt down. They're too small. Essentially, they don't build up enough heat, and their construction, their materials are such that they can't melt down. NuScale's design is, let me just go. Okay, so here's the core in NuScale. Again, it's a traditional light water uranium reactor at about 5% enrichment. So if all power goes out, you have no external water, no external power, no pumps, then the decay heat just basically for the first day is dealt with by the existing water. For the next few days to month, the residual heat basically boils off that water. So by that time, because again, it's so small, it's cooled off enough where it just bleeds off heat into the surrounding soil faster than it can build up. So you can never get to the point where it can melt down, again, because the surface area to volume ratio is so different, so small. Now, Nuclear Navy essentially has been doing small modular reactors for 70 years. They've had no problems with it. Russia had a problem because they used the fast reactor and they didn't understand about polonium leakage out of penetrations, but that's a whole nother story. So again, build them as fast as possible. The National Hydropower Association and the Department of Energy have a plan, it's a very good plan, to double hydropower without building a single new dam. Now, the reason we can do that, it turns out only 3% of our dams generate electricity, and you can electrify almost all the rest, all right? So here's the non-powered dams in America that could be electrified, could generate power, and this is their various size. So they, some of these can be very significant. We could double the hydropower capacity in America just without building a single new dam. And that's nice because these dams are already having EIS associated with them. Yeah.
Would that take a lot of steel or concrete?
Concrete, yes, but it's still good. Okay, it's still good because hydro emission is, I can't remember exactly, but it's about 20, grams of CO2 per ton. I'm sorry, ton of CO2 per gigawatt. So again, it's not bad. It's not as bad as solar. It's a little worse than wind and nuclear, but it's still very low. I mean, you're at double digits, not triple digits like fossil fuel. So you could do that. And the people already living near them are used to having a dam there. So again, the public outcry would not be very large just to electrify existing dams. This is a key thing we could do. Now, in the Pacific Northwest, I want to mention why wind is basically useless here. This is a load graph from Bonneville Power Administration that is the main system operator in the Pacific Northwest. Red is the load. So this is what's being drawn. This is the consumption that everyone in the Pacific Northwest is doing. So we as a people get up in the morning and we start firing things up. Things cool off during lunch, and then they fire up again, and then we go to bed. So this is the load curve of a normal week, right? Blue is the production from hydroelectric. So as you can see, it just follows the load curve. I mean, hydro is what does our heavy work in the Pacific Northwest. And it load follows the load. Okay. Now brown is thermal, so that's the single coal-fired power plant left in Centralia, a couple of gas plants, and the nuclear plant. And it basically they just tool along. They almost never go down unless there's a huge spike in something, and it goes down a little bit, but it's pretty much constant. And then green is wind. Now we have 7,100 megawatt capacity of wind in Washington State. And so when it starts blowing, you get this huge surge in power. And again, as I mentioned, consumption and production and delivery have to be balanced precisely. And so what happens is that hydro has to come down really fast. Okay, we just have to stop. We have to let the water flow over the dam and just forget about it. No power. And so all wind is doing is displacing hydro. So in the Pacific Northwest, you're replacing one renewable with another. You are absolutely making no headway in terms of climate change issues and decreasing emissions from the state because hydro doesn't emit very much. So wind, I mean, I'm not sure if I'm getting this point across, but wind only displaces hydro in the Pacific Northwest. You get that? And that's why it's stupid.
Yes,
Now,
you can kind of see that the thermal also dipped a little bit, but I mean,
yes, right.
Also
During this
mostly
one
a
thing.
constant line regardless.
Yeah. And when it does dip, only when there's a huge influx of wind, like on this day, but usually it's not that much. But even then, it dips just a tiny bit. So it's hydro that does all the heavy lifting.
Someone made a point in the chat that what if we were to donate our wind turbines to other areas that may potentially utilize them better than we could in our areas?
Yeah, Tornado Alley. Yeah, absolutely. I mean, that's what I'm kind of talking and pushing, is that there is a best place for all of these. Okay, I mean, geothermal is stuck with where the hot rock mass is at depth. Hydro is kind of stuck in terms of physiography. You need a certain change in elevation over distance to have hydro effective, but that's fine. Wind, you just need to have it in a windy place, and solar in a sunny place. I mean, that's easy. Nuclear can go anywhere. It's not weather dependent at all. So again, you need to balance this and decide where you want things to go to maximize their output for the money, because this is expensive. Now, if you read the latest E3 Northwest Resource Adequacy Study, they found that over the last several years, we have 7,100 megawatts of wind, but it was only providing 7% of that when we needed it. On the really bad days, the very coldest days, the very warmest days, you don't get much because wind does not blow on really cold and really warm days. And so one of the problems is that if you're going to be placing a lot of wind anywhere in America, when you really need it, it's not going to give you anything. And that, it's fine when you don't need it and it produces a lot of power. Okay, fine, that's great. But when you really need it, it won't. And that's what caused the blackouts in Texas and California this last year. Cold in Texas and warm in California. They just couldn't depend on any of the wind that they installed. And they installed a ton of wind over the last 5 years in both of those places. And it did not produce when they needed it. That's the problem. And their gas couldn't come up fast enough because they didn't have enough gas supply, not enough pipelines. Okay, another thing you need to do is secure sources of the materials, like I mentioned, iron, but cobalt, lithium. You're not going to build enough batteries for fully electric vehicles or for anything else if you don't have these metals, and we don't have enough of these metals. And the United States doesn't produce almost anything in this. We used to, but we closed them all down because China undercut the entire world. So, you know, it's kind of a boring issue, you know, where we're going to get the lithium, where we get the cobalt, but it's essential. I mean, absolutely essential. Because we need to, in America, we need to build at least 150 million fully electric vehicles to make any dent in oil consumption. And we need at least 100,000 charging stations in order to service a national fleet. And then we need to streamline the process to site and approve high voltage transmission lines. Okay, people don't like high voltage transmission lines. They say they want renewables, and then they vote down any attempt to put high voltage transmission lines. You're not going to get anything out of renewables if you do not have the high voltage transmission lines to transmit that energy to where it is needed. So we're building, you know, wind turbines in Eastern Washington and down the gorge. Hold on a second. And down the gorge, yet Seattle is the real need for that power. And so if you don't have high voltage transmission lines to get there, you won't get anything. And so again, it's very strange. Now, when you look at high voltage transmission lines, we usually think of AC, right? That was Edison versus Westinghouse. But it turns out high voltage transmission lines, DC lines, are much more efficient, and they even cost less over longer distances. So we have only built one large high voltage transmission line in the last 20 years. It was the DC line from Texas to Tennessee. So again, we are having problems because we're not coordinated. So if you're going to build a bunch of renewables, you better build a bunch of transmission lines, and the public votes them down every time we try. So, you know, this is one of those weird things. They don't understand that you need these if you're going to have renewables. So in America, this low carbon plan will require, and again, you can play with these numbers all you want, you can move them around, whatever, but on the order of 500,000 new megawatts of wind, 200,000 new megawatts of nuclear, 300,000 new megawatts of solar, and 120,000 new megawatts of hydro. If you do this and all the associated issues, you know, related to them, then you can replace fossil fuel. And this provides enough electricity for a fully electric fleet of engines. So, but how long to do this? I need 200,000 new megawatts of nuclear. That's not going to come online very quickly. We're going to have to start real fast and go real quickly. Same thing with wind and solar. I mean, we haven't produced anywhere near this, okay, a fraction of this so far. And 2040 is looming. Now for the world, it's even worse. You're going to have to come up with 4 million new megawatts of wind turbines, 1.4 million new megawatts of nuclear, 2.2 new solar, and 1.1 million new megawatts of hydro, given that the existing 300,000 megawatts keep running. So what we have to do in America is go from this, which is our present mix. Oops. Stop it, Jim. Go from this to this, right? This to this. And this is going to take about 500 million tons of steel just in America. And we don't produce even 100 million tons a year. So that's a big deal. Now, again, the American Society of Civil Engineers has said that by 2025, our infrastructure problems will cost our economy $7 trillion. That is not a trivial amount of money. So this $1.2 trillion infrastructure bill will barely address this, but it's a good start. There's no question about it. Now, fortunately, the energy sector is only about 300 billion of that. So we can deal with the energy infrastructure problems well. And if you look at the age of our capacity, essentially, so this is all of the installed capacity, all sources. it's getting old. I mean, these are mainly old coal and old hydro plants like Grand Coulee Dam, that kind of stuff. These are, again, most of the things that we built, 10 to 50 years ago. And most of the new stuff is renewables and gas. Nuclear is right in the middle, anywhere from 10 to 50 years old, and it's split evenly. So again, the infrastructure is old. We got to replace it. Almost all of it, except the big dams and some of the nuclear. Now, what's it going to cost to achieve this mix? And keep in mind, is the difference in cost sufficient? Is the difference sufficient to justify unethical decisions? So, okay, I know this is America. You got to make a buck. I get it. But do you have to become filthy rich at the expense of the environment and everything else? No. I mean, if it's just a penny or two a kilowatt hour difference, whereas the regional changes in cost are 10 to 20 cents a kilowatt hour, then what, that's okay. We got to pay for this, right? It's not cheap to decarbonize, and this is part of the cost. So what's it going to cost? So one thing, keep in mind that energy is the cheapest it's ever been in history. Okay, this is an interesting study by UT Austin. Again, in the old days, all power was chemical, basically. There's a little bit of wind mills and a little bit of water mills. But essentially, when the Industrial Revolution came about, boom, it became very cheap to produce energy. And it is cheapest right now. And as a result of that, food is cheapest right now than it's ever been in history. So if you're going to make these huge changes, now is the time to do it. Now, if we look at how much it's going to cost for a new energy mix, we'll use the Northwest Integrated Resource Plan, levelized cost per kilowatt hour. I hate levelized cost because it's not really real. It's got a lot of other weird stuff in it that has nothing to do with the technology, but that's okay. We'll use the numbers that the state legislatures use. So we see, yeah, coal is expensive, hydro is expensive. Nuclear is not that much more expensive. I mean, all four of these are within 1 penny a kilowatt hour of the mean. So, okay, fine. So you can't cry, oh, gas is so cheap. It's not really so cheap. It's cheaper. Sure. Yeah, Dave.
Quick question about that. Does the cost of nuclear power generation include the cost of waste disposal?
Yes, absolutely. Now, these others do not. Okay, nuclear is the only one that actually pays for its waste. So the Nuclear Waste Fund is enough to cover all nuclear waste disposal as long as we put it in the right rock. And that's another talk. It's not Yucca Mountain. Okay, we need to actually put it where WIP is. If we can easily pay for it with the amount of money already in the Nuclear Waste Fund. Yeah, so nuclear is forced to, and that's a good thing, to pay for its own waste. The others don't. And wind and solar is becoming a problem because their waste is also pretty nasty. And they don't have to pay for it. So it's just kind of weird. So, but we'll use these numbers, okay? And we'll go between now and 2040, how much is it going to cost to achieve a new mix? So if we look at where we'll be by mid-century, about 5 trillion kilowatt hours a year in the United States, with the present mix, if we keep business as usual, fossil fuels 2/3, everything else is 1/3, it's going to cost about $9 trillion, of which 1.7 trillion is capital investment. All right, that's just what it's going to cost, which is not bad, for 30 years. That is not bad at all. Now, if we go to this mix that I was talking about, 100% renewable nuclear hydro, it's going to cost $9 trillion, just like the present mix, except that 4 of that 9 is capital investment. Because now, instead of paying for fuel, fossil fuel, you're paying for things. You're paying for steel and concrete. You're building things. Okay, you're not putting this up to stacks. So, whoops. So if we look at the present mix, again, very little of it's capital investment. Like I was saying, gas plants are cheap to build. Coal is not that bad. Oil is cheap. So again, this 9 trillion is mostly fuel and not materials, whereas the new mix, most of this 9 trillion or more than half is capital, which is good because you get to keep that. That's nice. But the problem is capital investment has to come up front. So you're asking the people of America to fork over a lot more money up front in order to save it down the line. And of course, no one likes to do that. But it's still not going to cost any more to do this, right? What's important and is very little talked about is that this mix uses no fossil fuel, almost none. I had a little bit of gas left because we're still building gas. It saves 4 billion tons of CO2 a year, and the healthcare savings alone is about $4 trillion. Okay, there's a great study done by Canada that says if your society has a significant amount of coal and oil, then your healthcare your healthcare costs are increased about 10%. And for us, that's $400 billion a year. Okay, so over this time period, you're going to save about $4 trillion in healthcare costs. That more than pays for the capital investment. Yes.
And just when you say almost no fossil fuel, what it does use is fossil fuel to make the steel and the concrete, right?
Yeah, up front, yes, up front it does. But then we have to get to non-fossil fuel production of steel and concrete. Now there's some companies working on that. There's Eon Blue Technology has a non-fossil fuel way to produce chemicals and things like that. So yeah, that's a whole nother thing. And we have to deal with that. But you can't do it without first getting rid of power sources for fossil fuel. And then you can get into the industrial uses of electricity that's not fossil, heat that's not fossil fuel. Again, nuclear is perfect for that. Now, if you are renewable only mix, just renewables like people talk about, it's going to cost you 20 trillion. So it's going to cost more than double. And 16 trillion is capital investment because it's all about building wind and solar and renewable systems, so there's no fuel, it's all materials. And of course, that's way too much. That's absurd. Again, this uses almost no fossil fuel. So you have a $4 trillion savings in healthcare, but that is not enough to offset the $16 trillion in upfront capital investment. For the world, you're talking about 65 trillion by 2040 to produce 35 trillion kilowatt hours a year with no fossil fuel, and about 28 trillion in capital. And so that's why everyone's worried, because this is a lot of money. Now, there is the levelized cost of energy nonsense doesn't include a bunch of indirect costs. And so when everyone uses those numbers to compare nuclear and gas or nuclear and wind, they're not accounting for half of the cost. So things like California has so much solar and wind that they have gas turbines on idle, just waiting for when the sun goes down, they have to kick on. Well, you have to pay for those gas plants to idle, and they're not cheap. Okay, but no one ever adds that cost in. Well, there was this study that was done by IHS Markit that did that, and sure, right now for existing nuclear, it's 4.5 cents a kilowatt hour. For new nuclear, it's 6.9 cents a kilowatt hour. But for wind, it's 8.9 and 9.8. Now, one of the problems with subsidies, taxpayer subsidies, is that it doesn't reduce the cost. It just shifts that cost from the ratepayers to the taxpayers. So the people at the end of the month that get their energy bill, they don't see that, okay? Their tax dollars go to it, but no one knows where the tax money goes anyway. So it's kind of hidden. And that's, but it's still being paid for. Okay, someone's going to pay for it. At the end of the day, this costs money. And where do you want it to come out? Do you want it to come out of the ratepayers, or do you want to come out of the taxpayers? Then there's the indirect costs, the externalities. I don't know if you know that term. It just means someone's paying for this. It's not coming at the end of the month in your bill, but someone's paying for it. Polar bears, your grandchildren, whatever, someone's paying for this. And it's not usually something that is captured in any cost analysis. So the two things we usually do is we talk about the physical footprint, the area in square miles. So each little blue square is enough, is what it takes to produce 1 billion kilowatt hours per year from each of these energy sources. And then we talk about CO2 emissions. Now, CO2 emissions is kind of a proxy for everything, for pollution of many sorts, mining and all that kind of thing. So, but it's all captured in a CO2 per kilowatt hour. So each little brown square is 4 grams of CO2 per kilowatt hour produced. So, so as you can see, sure, I mean, oh, and also I put in the change in cost if we put a $15 per ton of carbon tax. Now, it's probably 15 per ton is not enough to make any difference. Who just did? Stanford actually, no, Berkeley actually did a study that showed, yeah, if it's not $40 per ton up to $100 per ton, it won't really make much difference, but that's okay. This just shows you that, yeah, fossil fuels, all about carbon. So their carbon footprint is huge. Their physical footprint is, no big deal. These are all about area. So renewables are all about area, not much CO2. And again, you can see this here is from cement mainly, and the larger CO2 from solar is from the manufacturing using chemical solvents, organic solvents. But wind and nuclear, not much at all. And all of that is from construction. But the area is very large for renewables. The area is not very large for nuclear. So if you're paying for these, nuclear has the least cost of externalities. Now, there's another thing no one ever talks about that's called the death print. So the death print. So I got to push coal off to the side because it kills so many people per megawatt hour. So each of the little red squares is 40 deaths per trillion kilowatt hours produced. So you have to normalize, right? This is all about production, not installed capacity. So as we see, yeah, fossil fuels, coal is the killer. If you need an evil, it's coal. Coal's evil. Okay, if you need that, okay. However, at the same time, you have to realize that it's raised 2 billion people up out of abject poverty, so you can't rag on it too much. Gas is much better. Hydro is much better. Now, these are global numbers, okay, not US numbers, global. And then, of course, when you get down to wind, solar, nuclear, no one ever dies. I mean, no one ever dies of nuclear, of course.
What's the death from hydro?
Flooding.
Oh,
Dam collapse. Okay, so the Bankyo dam collapse in, I think it was 76 in China, killed 170,000 people. So that's, when they go, they go. They don't go often, but when they go, they go. Now, if you look at the numbers, the actual numbers, here's the mortality rate, deaths per trillion kilowatt hours produced. For coal, global average 100,000. China, of course, has been very bad. But 5 years ago, this number was 250,000. So they're getting better. Now in the United States, we only kill 10,000. That should get a laugh. That's not good. I don't, it's better than the world, but it's not good. But oil, okay, same kind of thing. Now these are all particulate, pollution related deaths, air quality deaths, things like that. Biomass, the World Health Organization just put that biomass is a health epidemic in third world countries and developing nations. So this is not good for biomass. Basically, it's a ventilation problem. But then you get down to here, and these are simply accidents, okay? And you notice I have a global average, US average. So for coal, hydro, and nuclear, I have a US average versus a global average. And now why is the US so much better? Shout it out, anyone wants to.
regulations?
Yes, regulation. So the reason coal kills so few people here is because of the Clean Air Act. Now, the Clean Air Act is arguably the single piece of legislation that saved the most lives in the history of the world. Okay, there's a little debate whether it was the 1932 Labor Act or whatever, but still, the Clean Air Act is absolutely wonderful. That's why this is only 10,000. Hydro, look at that. Wow, 5. And those 5 are people that just fell off of ladders and broke their necks. I mean, it had nothing to do with hydro. It's because we have FERC, the Federal Energy Regulatory Commission. They actually check dams continuously. And if they see cracks forming in the cement of a dam, they will shut the dam down. They'll put a little coffer dam around it, and they will force the utility to fix that dam. We just did one out here at Peace Rapids Dam a few years ago. That's why now the rest of the world, a lot of countries don't have a FERC. They don't have a regulatory commission that's of any strength. So that's important. And then again, nuclear, and I threw in, Fukushima and Chernobyl, the worst case, not nearly that bad, but still the US, less than 1 a year. I'm sorry, less than 1 trillion kilowatt hours, which is much less than 1 a year. And why is that? NRC, the Nuclear Regulatory Commission. We have a very strong one, strongest in the world. And although people like to think they're in the pocket of industry, industry hates NRC because they'll shut them down for tiny little things. And that's okay. I mean, it increases the cost a little bit, but it means no one ever dies around a nuclear power plant. No one's ever died from radiation, certainly, around a US nuclear power plant, but no one ever dies of anything. When I worked out at the site here, I had to take ladder training. It was interesting. I didn't know that much about ladders, but you had to take ladder training, and you need 2 qualified operators to operate a ladder. Do you think anyone ever falls off a ladder at a nuclear power plant? No, they never do. But in every other industry, they do, because they're not focused on safety like the nuclear industry is. So anyway, so with these numbers in mind, it's kind of hard to argue that nuclear is dangerous. Or more dangerous than anything else. Now here's Beijing, which is 80% coal. Okay, the rest of the country is only about 66% coal, but Beijing is about 80% coal. They're trying to clean it up. Now what they've done is put in large screen TVs, because it turns out it's very depressing if you never see the sky for weeks at a time. Kind of not what I would do, but hey, it's interesting. So I want to finish this off with what's the most dangerous thing on this list? Or what are the top 5 or so? Anyone want to shout out? Everyone shout out.
I'd say automobile driving.
That's in the top 5.
Smoking tobacco.
That's in the top 5.
Coal industry.
Murder?
That's up there, unfortunately, but not the top 5. But yeah, it's way high.
Alcohol consumption.
Skyrocketing.
Yeah. All right, let's look at the numbers. Okay, woo, hey, this is bad. Yeah, so this, these are the top. Now you might say, what's iatrogenic? Well, iatrogenic is medicine gone wrong. It's not malpractice or abuse. That's down here in opioid deaths, but it's just don't know why the patient died. Okay, it's actually quite a big killer because we're all getting old. Now, what's funny here, food poisoning, 25,000. Holy mackerel! And this is, I averaged it over 5 years because I wanted to smooth out the bumps and the hills. Now, a biostatistician gave me grief recently because he said I hadn't normalized to the subpopulation. Okay, smoking is still the worst. Iatrogenic falls to 3rd. So this is, this is just a rough danger index. You just divide the number of deaths by the population involved in this. So yeah, so mining only has 360 deaths, but there's only 350,000 miners. So that moves up quite a bit. Now, it's nice to know that eating is only slightly more dangerous than nuclear power. That's good. Okay. So again, these are the numbers. It's hard to argue that nuclear is so dangerous. It's horrible. It isn't. But even non-lethal routine accidents like falling off a ladder that I mentioned, it's safer to work at a nuclear power plant than it is to sit at a desk trading stocks. Now, this is OSHA data. And that's because when you're sitting in an office building, you don't care about safety. You're not thinking, you care about, but you're not thinking about it. So you'll stand on a rolling chair to hang a picture. Okay. We do that. Okay. Not in the nuclear industry, we don't, but in industry. So, and you fall and you break your arm, it gets reported to OSHA, and that's what these numbers are for. Now, yeah, the steel manufacturing is a dangerous job. There's no question about that. But nuclear industry, safest industry in America. Nothing like it. So why are we so afraid of energy?
Simpsons.
Yes. Yeah, we told you to be. I sorry, my bad. But yeah, we've been saying how dangerous it is with no data backing it up for decades, because ideologically it seems bad. All you have to do is mention nuclear and mushroom clouds appear in the brain. And so it's really hard to talk against that with a bunch of data, because data is boring. But in the end, we need to know this. And we're not very good at communicating that. Okay. The real reason, of course, is we have incorrect but intentional association with nuclear weapons. The whole idea of the Cold War was to scare everyone about nuclear, and it worked. It worked. Okay, we kind of got lost the subtle difference between, or not so subtle difference between energy and weapons. Inaccurate, purposefully simplistic modeling. I don't know if you've talked about the linear no threshold dose hypotheses, that every photon of energy is going to kill you kind of thing. It's stupid. It's not true. But we adopted that as our regulatory guide in 1959, the whole world, and it's wrong. Okay. So it makes everyone afraid of radiation when they shouldn't be. It takes a huge amount of radiation to do anything. And it's very hard to get that. And then, of course, misunderstanding of the nature and the amount of nuclear waste. Okay, there's not much of it. All the nuclear waste in the world ever produced could fit in one decent landfill. That's it. But, solid coal waste, wow, produces it every year. So, and we know what to do with nuclear waste, as I mentioned. We're just not allowed to. Thank you. I hope that was useful.
Wow, that was amazing.
Oh, good. Thanks.
You guys want to give virtual round of applause for Dr. Conca? That was so cool.
Oh, good. Thank you so much. That's good. It's great stuff. I mean, it really is the subject.
I know we're way past time, but do we have an opportunity for a few questions?
Sure.
So you've made an incredibly compelling case for nuclear. And so I have two questions. They're related. It seems to me the most compelling argument I've heard against it is that the difficulty of quickly enough ramping up nuclear. So
we did it in the 70s.
So I'm curious. Yeah. So I'm curious. With the right political will and the right amount of money, could we? How long would it take? And then associated with that, and this is my more pertinent question. So if someone you've persuaded me as a citizen, as a teacher, that we ought to move in the direction of increasing our nuclear capacity, what should individuals and activists do to encourage and to create the political and social will to move in the direction of nuclear?
Right. I really thought, I'm not sure why I did it, but I really thought climate change, and people like Jim Hansen saying we need nuclear would actually sway environmentalists who depend on the climate change scientists for the urgency. And it hasn't. Again, it's an ideological thing. And unfortunately, on mainstream, TV, I mean, I love MSNBC, but whenever they have a nuclear person on, it's not a scientist or an engineer, it's an activist. And it's like, wait a second, there's lots of us out here, although it's hard to get known, all right, because we don't have the resources, that the anti-nuke folks have. Most scientists are working. They don't have time to go out and be activists. Yeah, so it's kind of funny. How do you reach a lot of people? That's the trick. And I don't know how to do that, because education is it, but it's slow, right? And we don't have the time to be slow. Peyton, you had a question.
I kind of have a few questions. So, you're that graph showed that like we're not anytime soon gonna go down. I was wondering, like, so is going into the nuclear industry, like, is this going to suddenly become a big deal, or do you think like this is going to continue, like CO2 emissions are just going to keep going?
Well, I'm afraid, I don't want to be pessimistic, but I'm afraid they're going to keep going. And then we have to have a plan B. And you have to get me back to talk about plan B, which is solar geoengineering.
All right.
Which is something UW is very good at. Yeah, so we're going to have to take a little bit more active participation in changing the atmosphere. I hate to say that, but we aren't going to decarbonize. I mean, we're running up against these walls, and every time something happens, people choose fossil fuel, because you can't ask people to remain in poverty, right? I mean, you just can't do that, because you care about the planet. It's like they're starving. They need energy. And so they're going to get it. And that's always been the problem. Humans first, environment second. And that's going to continue, even though we understand this better, but it's easy for rich countries to try to do this. It's not so easy for poor countries. And most of the people on Earth are in poor countries.
Oh, sorry.
Oh, good. Actually, I didn't realize I'd gone so long.
Oh, that's okay. As long as you're fine with answering a couple questions, we're happy to keep you here for a little bit.
Okay, how about one? Can I do one more? Because unfortunately, I have to take off.
Yeah, of course. Yeah.
Go ahead. Go ahead. Sorry.
Peyton, did you want to ask your second question?
Sure. So a couple of my club members were talking about thorium. And I wonder if you had any opinions on that.
Love thorium. Yep, thorium's great. It's more abundant than uranium. It's not as fissile, so you have to have a uranium, an enriched uranium trigger, basically, to get it going, which is fine, and that's good. One of the problems with all these alternative stuff, like the fast reactors, natrium, the pebble bed reactors, thorium reactors, molten salt reactors, is that NRC doesn't know how to license them. Okay, all they've ever licensed is a light water reactor, ever, right? Yeah. So if you go to NRC, so that's why NuScale, I'm really betting on NuScale, because NuScale is a light water reactor. It's nothing different, really. It's just smaller. There's a few little things in there that are quite different, but they've been sitting on NRC's door for 10 years, giving them everything they need to know. When the first molten salt reactor license gets delivered to NRC doesn't have any personnel to evaluate it. So they're going to have to hire and train people. That's going to take years. So the licensing problem with thorium and molten salt and everything else are large and lengthy, simply because they have not done it before and NRC doesn't know how to do it. Okay, that's kind of a weird administrative thing. It's not a technical thing. It's just a weird administrative need.
Yeah, that makes sense.
Yeah, but we have tons of uranium. We have lots of uranium.
All right, I will let you go, Dr. Conca. Thank you so much for this presentation. It has been so informative, and I think
thank you.
We'll have some questions for you. If you're open to having one email sent, like we could craft it and maybe send.
Oh, sure. And don't just do as many as you want. That's fine.
Okay, I will have all these people email their questions. Good. We'll send you an email over with that. And then also, could we have your presentation, your slides? I know we're recording, but are you willing to
oh, sure. Yes, and Stefan someone bugged me, okay, because it's a large file. I need to chop it into pieces to send it, but that's okay.
Sure.
That's good.
Sounds great. We will have Stefan be in touch with you. And yeah, thank you so much. It's been great. And I thought your jokes were funny. I just had to be on mute, so I couldn't laugh out loud for you. But
Yeah, you have to make it funny. Yeah,
It was great.
nuclear
Yes.
waste is fun. Nuclear waste is fun. But yeah, so do that. Also visit, just Google Conca, Forbes, and then whatever subject, and I'll come up. So
Awesome. Great. Thank you so much. Thanks to
Thank you.
everyone attending.
Thank you.
wonderful.
Okay.
So great to
Nice,
have you.
nice audience.
Thank you.
Thanks.
Thanks.
Thank
Bye.
you so much. Take care.